Hi and welcome to the last video of Automata. This is my test number 3. Oh, and also I forgot that I have to do my final, but yes, welcome to the last test before the final. My name is Juan Garcia and we're gonna talk about all the 8 problems. We're gonna talk about them chronologically, and it will be uploaded directly to YouTube. So we're going to the first one, which is the design the Turing machine that given a positive unary number adds 2 to this number. So I'll go by step. It's pretty much easy. So we already know that we have an input of n, but in this one it's bad. It should be 2 instead of 1 because we're adding twice. So we're at the start point. So we're let me go to. Yep, that should be better now. So we're at the start point. So when it's empty, we move to the right. And we see a 1, we move to the right. So when we see a space, we move to the right and we replace. So we will be replacing. Sorry, I received a message from Dr. Diego. So I will be replacing 1. Uh, so I'll add 1 here and then go to replace 2, which it's going to the left and also replacing 1, and the back 1 should be just going to left, because when you see a 1 you're just going left and you're going to the rewind, which is the halt. So this works also. This should be 3. It's working also with 2. So if you go 2, you go to the second space, you add 1 and you add 1, and that should be it, because you're adding instead of subtracting. So that one was pretty simple. The second one was also very simple. It was, let me go, yep. So design a Turing machine that giving 2 unary numbers compute their sum, tested step by step. So I asked that one to my TA, and it was kind of tricky, but it was kind of also. So it's pretty much what you have here. It's that you have one variable here, and then you're going to add the other variables to your tape, and then you're gonna rewind it. So first of all, you're going to the start state. Yep, that should be fine. You're going to the start state, and then when you see a 1, you go to the right, because you already know you're passing your first move, and then you're going to your second move, and then you go keep 1 until you find your stop. So when you see the space 1, you go to the left and you replace that one. You replace this one with an empty string. So it should be going here. So when you see a space 1, you go to the left. So when you go to the left, you're going to replace 1. You're going when you see a 1, you're going back, as it says here. When you see a 1, when you see an empty one, you're going to sum, which will go 1. And then when you see a 1, you go to the left, and it should be just L. That should be fine. And when you see back, you see a hold. So that should be fine. I'm trying to trace it. I'll pause a little bit because I think I have a problem between sum and replace when I'm moving, but when I'm doing the replace 1, I'm going to the move. So so it's fine. It's fine, because when we're going to the replace 1, which is the one we see here, we're taking the sum 1. So when you see a 1 in sum, you're going back. You see a space between them, you add a 1, so you're going to back, and back is rewinding. So that's for number 2. Plus, let me read number 3, which is designing a Turing machine that, giving a positive binary number, multiplies this number times 2. This is really easy. The only thing that was um, kind of hard was just to think about when it should be uh, how to multiply the binary number in order to be 1, 2, 2 to be 4, 4 to be 8, 8 to be 16, 16 to be 34, 32, and so on. So what I did, it's pretty much that. So I'm going to, yep. So I'm going to start at the space and going to the right with to the move. So if I see a 1, I'll convert it to 0. I don't see one. I'll pass it out, go to the right. I'll pass it out and see a 1. I should convert it to a 0. Should go here. So when I see a 0, I still go right. You're going to the right. You see a space, you switch it, and you're going back to rewind it. So you see a 0. You left, left, left until you go halt. And that's for number 3. That's pretty simple to that one. Let me go to number 4. The number 4 was the kind of tricky one that I had to ask Dr. Diego. It was really, really simple, but the thing here is that we have to read carefully in order to know what's going on. So we have to design a Turing machine that determines whether or not a given binary number, which is the your first bit is going to be the least one. It's a multiple of 2. So you already know if it's a multiple of 2, if your least number it's 0, in its odd number if it's 1. So that's our main algorithm we have to know. So you don't need to transition to a halt state nor rewind state. So it's pretty simple. We're in blank. We see a 1 0 1, which is 5, which is 4 0 1 5. So if you go into the start state and you see a right, you go to the move. If you see a 1, you go to the left and you reject. This is your reject state. So when you see a 0, if here was a 0 that I have the choice here, you're going to the sub state and you go to the right. You don't have to rewind it. So when you see the left, when you see a 1, you go to the left and you reject. This is the 5 and this is the 4. So that was pretty easily done. Now we're going to number 5, which is a kind of just a question in my own words of how feasible algorithm works. Feasible algorithm is just a simple algorithm that you can answer, or you can go to to the to an answer to that. However, some of the times this is not true because I explain here, and I'll read it up because I think it's really helpful. But I believe that the algorithm has to be simple and good with practical, so it has to be done with the available resources you have. However, some of the times this is not true, and this is because you cannot create different examples using the same algorithm. So for example, you have 1 plus 1, it comes 2. So you have an operator and you have 2 operands. But what happen if you have a negative 1 plus 1? So you already don't know what's going on because you haven't seen negative numbers in your life. So this is why the feasible algorithm shouldn't be always an answer, because some of the times you already don't know what you're doing, even though you already have the resources of it. Because sometimes they can give you a new operand or a new operator that you won't use, or a new algorithm that you may change or you may keep depending on what you are doing. So, for example, in the example we have the negative number. The trick, for example, using the same algorithm, for example, an algorithm that will add any number and give a positive number. However, I did not handle the negative numbers, so or I create a new algorithm. This is just bad grading. A new algorithm, or I will just have to change my rules of my algorithm in order to see what's going on in there. So we're going for number 6. My bad. Uh, Number six, it's pretty easy. Really, it's just adjust the general algorithm in automaton to transformer into the Turing machine. So when we're in the start state, we see a plus or a negative, we're going to the intermediate state. If you see a 0, 1, you go to the final state. If you see the intermediate state 0, 1, go to the final. Plus or negative, go to the sync. Final 0, 1, go to the final, which is going to be a loop. And the plus or negative going to the sync. So the only one who's not going to the sync from the start because he's going to the it's going to the intermediate state and the final state. So pretty much this is my this is the PDA you're giving. Yeah, this is the PDA you're giving. This is the automaton, and this is the rules, the Turing rules, which is real simple. Let me show them to you. So when you start and you see you're going to the right and you see nothing, you're going to the start state. When you're in start state and you see a 0, you go to the final state. When you see a 1, you're going to the final state also. If you see a positive negative, you're going to the intermediate state. You see intermediate state 0, 1, and that's so going on. So as we know, we only have one step state. I'm waiting to see if yeah, should we have only one step state? So my reject state should be when I'm in sync. Let me try to put it here a little bit better. When I'm in the final state, this should be accept state. When I'm in the intermediate state, should be rejected, and when I'm in the start state, should be rejected. And this is my I create a kind of array, letting you know in which states they are putting in. So my start state, it's going to be the plus, which is I'm giving, going to the intermediate. When I'm in the intermediate, I'll give a 0 and I'll go into the final state. When I'm in 1, I'm in the final state, I should receive a final state. So that should be correct. And lastly, I'm going to the 7, which is the polynomial, non-polynomial, the non-polynomial complete, the non-polynomial hard. I pretty much gave the idea, so well, yes, the polynomial is a problem that can be having a polynomial big O notation, which could be easily to solve and during immense runtimes. The non-polynomial problem is a problem harder to understand, and the running time could not be polynomial, but it can be polynomial, so that's why it's inside this diagram, because P can NP can be P, but P can be NP, but NP not always can be P. So when I'm in NP complete, we see a time. This is because they are having their problems that live in both NP and NP hard classes that are verified in polynomial times, and that any NP problem can be reduced to a polynomial time. So this is this tiny piece of non-NP complete. So when we're in NP hard, there's an algorithm solving that can be NP problems. This means that at least as hard as NP problems, but it could be more complex. So these ones can be really complex. So I think I just have to explain uh, the ways to do it, or the ways to think about the PNP, NP complete, and NP hard, and I'll give some diagrams of it. So the last one is, in my own words, what's the church Turing thesis? Is it a medical term? No, it's not. It's a physical problem. It's a statement about the physical world. Yes, it's a statement about the physical world, because in the description of the church Turing thesis said that anything that it can be computed into a computation device can also be computed in Turing machine. So as it's hardware, we must say that that is in the physical world, and it's not a mathematical theorem because this is we're talking about. So mathematical is about a mathematical system, so it can be true. if you're using newtons, but it should not be true, or we don't know if it's true if we're using the quantum universe or the quantum science we're having it. So we don't know yet. So we don't know yet if the Schur Turing test can be good with a quantum. So that should be it. Just last 15 minutes. I hope it helped, and I upload it right now. Thank you very much.